All right, looks like everybody got a chance to join, so let's go ahead and get started. So good morning, good afternoon, and good evening, everybody. I would like to welcome you to our webinar today. We're covering the topic of hardening your CICD pipelines with GitOps and continuous security. Richard, could you flip to the next slide, please? I quickly want to go over a few housekeeping items. So this call is being recorded. We will share the recording afterwards. At this time, everybody is in listen-only mode. So if you have questions, please use the Q&A panel throughout the webinar to submit your questions, and we will answer those at the end during our Q&A. All right, next up. So I would like to introduce our speakers today. We have Owen Garrett on the line, Head of Product and Community at Deepfence. Hi, Owen. Thanks for joining us. And then we also have Richard Case, our Tech Lead and Solutions Engineer here at Weaveworks. Hey, Richard. Cool. And with that, we won't delay any further. Richard, over to you. Take us through this, please.
Brilliant. Thank you. So I'm going to start with what is GitOps as a refresher to anyone that isn't fully aware of what GitOps is. So first and foremost, GitOps is an operational model. It defines a way of operating your systems, whether that is Kubernetes clusters or your infrastructure. It's derived from knowledge that was gained internally initially in how we, as Weaveworks, operated our SaaS called Weave Cloud, and further enhanced with custom work from customer success over the years. And it's technology agnostic. Obviously, the name has Git in it, and it's usually used, and we usually use Git as the source control within GitOps, but it doesn't mean you have to use Git. You can use any flavor of source control that you want, and it doesn't imply that you use a particular GitOps agent. There are many agents out there, and so it's technology agnostic. It also doesn't imply that you are going to be deploying to Kubernetes. It is a methodology and an operational model. And at the core of it, there's a set of principles that we will be covering later on. So this is basically saying the why instead of actually how you accomplish this. Although Weaveworks can help you with the how you actually accomplish GitOps, and we have Flux, which was the first GitOps agent or solution, which is open source and is now in currently version 2, which has many benefits and new functionality. And talking of which, if we go back to the most recent CNCF technology radar for continuous delivery, Flux is the only solution that is GitOps in the adopt section. And what does this all add up to? Well, it's a way to speed up your team, and this can be the engineering team or the operations team, and that's a fairly loose sentence. So some actual numbers from feedback from a customer of ours, which is Metal, which is a bank that was set up by NatWest, was deployment speed was 50% faster. And this, more importantly, which was the deployment frequency was up by 75%. And the mean time to recovery went down to 20 minutes. So for a bank, this is really important, that mean time to recovery. So we have a whole white paper on this if you're interested in more of the actual numbers of the benefits of GitOps. So what is the GitOps model? So traditionally, when we deploy to a Kubernetes cluster, we do the equivalent of a kubectl apply. That might actually be an operator sat on a keyboard typing the instructions manually, or it might be orchestrated via some sort of CI tool or script. So this implies that operator has direct access to the cluster, and essentially they are privileged. They have cluster admin rights, and so it follows that if you exploit that mechanism, then you essentially have exploited the cluster, and then any other clusters that operator has access to. So from a GitOps point of view, we don't like that direct access model, whether that is orchestrated by some CI tool. So we say, no, we don't like that. So in GitOps, everything starts from that declaration. So we declare or describe how we want our system to look. So we're not doing imperative steps saying, hey, do this step, then this step, then this step. We're just put in the declaration of how we want our system to look. And in this example, we'll use a Kubernetes cluster. So essentially, we are creating our Kubernetes YAML files and our manifests. So that's the starting point. We have how we want our system to look like, our desired state, for want of a better phrase. So that desired state is committed to some sort of source control. In this instance, we're going to use Git because it's called GitOps, but that could be whatever you choose. But because we're treating our desired state, we're committing our desired state to version control, and it's versioned over time, we can actually see how our desired state changed over time, what changed, when, and who made that change. This is very, very important to understand the changes that will apply to a system, especially in a scenario where there are issues or runtime problems. You can go back directly to the version desired state and say, oh, this change was made on this date, and try to correlate and help investigate. And that has an added benefit, is if there is an issue and you know what has been changed, you can roll back by simply doing a git revert. Or if the policy says you've got to fix forward, then you can just see what the change is and revert that change with another commit. So we have our desired state versioned in Git. So next we need something that actually understands that, and essentially we have an approval process. So what I'm talking about here is essentially a PR. So we've made a change to our desired state in Git. We want to apply it, so we create a PR within our Git repo. So as soon as that is approved, that desired state is applied to the target system, and that desired state and the actual state are brought in line together. And there will be a software agent that does that. But this point of approval allows us to run additional checks or implement additional policy at that point. So this is a production system, so we require 2 sets of eyeballs to approve that change before it goes into production. And now this is where GitOps gets really interesting. That agent that runs within the system is constantly monitoring the desired state and the actual state of that system, and it will alert if there's any divergence from that. And additionally, depending on the agent, as well as alerting on that divergence from actual and desired state, it will remediate that state as well, bring it back in line. And this is a continuous cycle as well. So it's not a one-time apply. It is a continuous cycle to ensure that there is no divergence from desired and actual state. So when we talk about Flux specifically, our GitOps agent, our open source agent, we operate this slightly different. Our agent runs within the cluster, and it pulls in the desired state from outside. So it's not a push-based model. It doesn't have the credentials to push into the cluster. It's already running in the cluster, and it is monitoring that desired state from outside. And this provides a very, very clear security boundary between what is allowed to deploy into a cluster, i.e. itself, and what is not, nothing else. So all operations are therefore then carried out by committing changes to that desired state repo. So if I was to summarize the principles of GitOps just from those previous diagrams, so we declare everything as YAML. So that's our desired state. We declare that. That desired state is committed to some sort of version control, Git in this instance. Then we have some sort of approval process for changes to that desired state. So think of a PR here. Once that PR is approved, that state will then be, that change in desired state will be automatically applied to the target system, Kubernetes in this instance. So, you know, the deployments will be applied to the cluster, and then the agent that's running will constantly monitor the actual state within the target system with that is declared within your source control system, and alert if there's any difference and take corrective action. So we see GitOps as an operating model for cloud native. So everyone's pretty familiar with the continuous integration. cycle. So we build, we test, we build, we test, and that's all with Git at the center for our source control. So we've basically applied the same to the CD part of the story, and we have Git at the core of that GitOps deployment. And this means that we are using Git. We're using, the engineers are using Git, the operators, the clusters are using Git. We're using the same technology, but it provides a clear separation of concerns. Even though Git is at the center, we can have whatever CI tool we want to do our continuous integration. But then we have GitOps that is only taking care of the deployment into the cluster. So we have tools that are dedicated to each job. We have a tool dedicated to CI, and we have a tool dedicated to CD. We don't have a CI tool trying to do CD and pushing things into the cluster. Because we're using Git at the center of all of this, we have the auditing capabilities out of the box. So we can see what changed, when, and why, which is great for any type of environment where you need to have that auditability, can't say the word, and transparency of those changes. Because we'll already be using Git for our source control, we would already had authentication set up. So we will have SSO set up to Git for our source code. This means that we can use that already set up authentication to prove who can do deployments. And then from the authorization, so who can actually deploy to this environment, that also comes with the fact that we're using Git. So the authorization can be the very fact that you have access to a specific repo that represents the desired states of that environment. And that could be separate repos, protected branches, etc. It depends on your Git flavor. And because we have this versioning of our desired state over time, this allows us to easily roll back changes that have caused issues, because we can just do that Git revert. And it also has this added benefit of helping with the DR type scenarios. In a traditional model where you have a number of pipelines pushing applications into a cluster, if you have to rebuild that cluster from scratch, then you have to create the cluster and then run all of those pipelines individually to get back to that state of that cluster. Whereas with GitOps, because you have that desired state in the repo, you create your cluster, deploy the GitOps agent, point it to the desired state repo, and then all of those applications will be reinstalled automatically. You don't have to rerun, 5, 10, 20, 100 different pipelines. So let's have a look at how we do secure deployments with GitOps. So this diagram just represents a typical CI/CD pipeline. There's a lot of detail removed from this, but it's just to give an idea. So really what it's highlighting is that there are essentially a number of credentials that are used throughout that CI or CD process, and they can be shared around, and they can cross what we call logical security boundaries. So to give an example here, so we develop our application, and then we have read-write access to the code repo to commit our code changes. So when our code changes, we have some CI tool that is monitoring that, and we'll create a build. So that CI tool has read-only access to the code repo. As part of that CI process, we are going to generate a container image. So that CI tool then requires read-write access to the container registry to push the image to the registry. So in a usual pipeline scenario where we're doing CD via some sort of pipelining tool, that CI system also has the read-write credentials to the destination Kubernetes cluster or environment. If you're using GitOps, not for Kubernetes. So in this scenario, those credentials are crossing a security boundary here, this logical security boundary between the target environment and our CI environment. So that's not ideal. As mentioned before, if you if you compromise the CI system and the credentials there, then you have access to every single cluster that the CI system has access to. And Gartner actually recently said that that is one of the increasing attack vectors of gaining access to clusters. So let's see what difference GitOps makes to this. So the change when we introduce GitOps into this type of scenario is essentially two things here that you can see. Well, three. So the CI system isn't doing the deployment first and foremost. So we've deployed some sort of GitOps agent into the cluster. You can use Flux in this instance. And we have introduced this configuration repo that is going to hold our desired state. So this is going to hold everything. It's going to declare everything that we want to run in that cluster. So the GitOps agent, Flux in this instance, will have read-only access to that config repo, because that's all it needs essentially to run. So it's going to be monitoring that configuration repo, saying, what is my desired state and what is my actual state, and then it will reconcile the two and do any deployments that have been declared in there. So Flux can actually run in write-back mode as well, which you'll see later in one of the demos, where it can actually update the desired state as well on changes to the container registry. But by default, it operates in a read-only mode. So in this scenario, what you end up with is the only thing that has rights to deploy to the Kubernetes cluster is the GitOps agent, or Flux in this instance, and that is actually running within the cluster itself. So actually, to get something deployed, the operator, whoever that is, they will have to make changes to that configuration repo. So they don't make changes directly to the cluster. And this traversal between the operator and the configuration repo, which is essentially going to be a PR on a branch of some sort. And this is a single point of where you can implement some sort of process control, process enforcement. So you can at this point say, well, I require 2 people to approve this deployment, or I require that this application must have been deployed in all of the lower environments first. So it's a single point of implementing that process control. And because we're using Git, as we mentioned before, we have this this really good auditing and attribution of changes within the environment. But that's not the whole story. So we can apply, things like RBAC or network policies via this. Create our, try and create as secure as possible cluster. But that's still not enough. So this pipeline offers various points where we can integrate extra security measures. So the first part is in the CI portion. We can introduce various options for code scanning or image scanning, whether that's on static code analysis or actually scanning of the container images within the registry. But we can do that in many places as part of the CI process. We could also do some sort of artifact scanning when we change the desired state within the configuration in the config repo. So we could use something like conf-test to run some essentially OPA policies against your Kubernetes YAMLs, or we could use something like kubesec. So these are all combining just to help secure our applications, but these are all point in time. At that exact moment in time, they're only doing the checks. We could also implement some sort of policy from within the cluster. So we could use OPA or Caverno or some other solution to actually say at the point of applying our YAML into the cluster, run these checks as well. But again, that's a point in time. That's a point of applying that change. So we could have an application that has been deployed into the cluster and been running for days or weeks. And then some sort of vulnerability has been found. There's nothing within this that would stop, would detect that at this moment in time. We would need to do another deployment, or we would need some sort of runtime scanning, and that runtime scanning has to be continuous because things change over time, especially since it's being deployed into the cluster. And this is a good moment to hand over to Owen.
Thanks, Richard. So the GitOps pipeline is a wonderful way to segregate the security of your keys and tokens to give you the maximum possible separation of concerns. But as Richard described, there's lots of opportunities to layer additional security measures on top, whether it's in the CICD pipeline, whether it's in a check before a container gets pushed into production, or indeed checks as containers and services are running on the production platform. And this is a challenge that at Deepfence we've been looking at for a number of years. Before I go in and we'll run through a couple of demos, show you Deepfence working within the GitOps pipeline that Richard explained, let's just talk about the need for security. It's often much, much greater than the people we talk to appreciate, because in today's worlds, there is an increasing number of interconnections between the applications that we build. Synopsys identified that in the applications that they surveyed, there's typically over 500 discrete open source components within those applications, both direct dependencies that are directly linked, imported into the application, but also the transitive indirect dependencies that are required by the direct ones. GitHub surveyed a number of repositories within GitHub, obviously, measuring the number of direct and transitive dependencies, and they saw it was not uncommon for every direct dependency to then pull in between 2 and 10 other modules or components. JavaScript and NPM was particularly prone to that, with an enormous explosion of typically 10 direct dependencies pulling in almost 700 transitive dependencies. And many of these dependencies are owned and operated by individual developers, or maybe in some sense abandoned, not kept up to date. They haven't seen security updates or even code changes, contributions within the last 2 or 4 years. In NPM itself, GitHub estimated that about 50% of the modules in NPM were owned by a single individual private developer, rather than a team or a corporate group. And of course, when you're building an application that pulls in those dependencies, whether direct or transitively, you're then taking on the risk and the responsibility for the security of those dependencies. And if it goes wrong, it can go terribly wrong. The Equifax incident, when they failed to identify that they were using a vulnerable version of Apache struts, resulted in 140 million customer details being leaked through an exploit. And the cost to remediate their security after that came to well over $1 billion. That's work which they probably should have done anyway, but the attack and the vulnerability threw that into sharp relief. It's not just the challenge of individual packages having particular vulnerabilities that are known, weaponized, and exploited, but misconfigurations, unexpected anomalous traffic could be an indicator that something strange is going on within your application. Capital One, misconfigured mod security. Mod security is a complex, difficult to get right web application firewall. And by misconfiguring, they enabled request flows they didn't intend. One such request flow hit the instance metadata API on their cloud instances, and an attacker was able to exploit that and over time leak over 100 million customer details. Third parties have accessed services and file systems, made unauthorized changes. British Airways suffered from that when a JavaScript component that they were using on their booking system was hacked, and that resulted in an enormous number of stolen credit card details. And if you want to appreciate the effect, the fan out that one individual module can have on the entire ecosystem, You just need to look at the NPM registry and the story about the left pad module that was pulled by its developer as a result of what was essentially a copyright dispute with another entity. And he pulled his module, whether in a fit of pique or because, for good righteous reasons. The knock-on effect was that tiny unregarded module had an enormous blast radius across many large web applications. So this degree of interconnectivity means that the security of applications is critically important. And by including third-party components and modules, you then take on the responsibility for the security and the correct configuration of those on behalf of your users, your clients. The next slide. If we look at how vulnerabilities are addressed, it can take a very long time for a vulnerability in a piece of open source code first to be detected. GitHub estimated that the average time to detect a vulnerability in an open source component was over 4 years. So undetected likely means it's not being exploited at the time, but of course, you don't know whether in some way it's being exploited and it has been weaponized. But even once alerted, it can take time to find a fix, to publish it, and then to push that out and users to pick that up. Sonatype in their surveys found that 49% of organizations would remediate an open source dependency vulnerability within a week. But that means that more than 50% of organizations are taking more than a week to remediate a vulnerability. So protecting yourself from pushing vulnerable code into production is critical. And being able to detect that code when it is running in production, when a vulnerability is discovered, is equally important. Applications contain potentially a time bomb of unannounced vulnerabilities, and any tools that integrate with your GitOps pipeline and allow you to find and respond to those vulnerabilities are invaluable. At Deepfence, our next slide, Richard, we provide a full lifecycle security solution. What I mean by that is that we observe and secure your application from development within the CICD pipeline through to its deployment into production and its operation in production. And we can talk through the 4 stages where you'll want to insert security in the GitOps-like fashion. In the first stage, so Richard explained how you can insert additional steps, tests, security measures in your CI process. And Deepfence's threat mapper component can be triggered by your build and test infrastructure, by GitHub Actions, for example, to scan code as it is built into containers. And we match that against wide lists of known vulnerabilities and can block the deployment of a push if that code fails to meet the parameters that you, as the developer, have defined. Once the code has been pushed to the repo, we can then scan the code, app containers, and applications within the repo in order, again, to match them against a series of known vulnerabilities and threats. And you can use this intelligence to help either guide the deployment of an application into production, or once the application is in production, to synchronize what's in production against what you know about vulnerabilities in the repo. In production, whether you're running in staging, production, DR sites, whether you're running virtual machines, you're running Kubernetes, or you're running serverless, then the lightweight Deepfence agents are there to scan the production environment, looking for anomalies, misconfigurations, leaked or unprotected keys, and reconciling what it sees in production with what is sitting in the repo. The agents also monitor the behavior of applications and feed data to your operations team, flagging up anomalies, unexpected network traffic. Maybe a container is trying to access that instance metadata API that it shouldn't be. Identifying unexpected file system modifications. Maybe somehow the JavaScript that you're using on your British Airways site is being modified. detecting unexpected process creation or system calls. So together, these solutions integrate very cleanly with the hands-off autonomous GitOps pipeline that you've built and provide a multi-layered set of security measures to increase and enhance the security of your apps. What I'd like to do is hand across to my colleague Matt, and we'll go through and we'll see the GitOps pipeline in practice, and we'll see the process of deploying, inspecting, protecting an application using Flux and Deepfence.
Thanks, Owen. So let me just quickly introduce myself. My name is Matt Krishak. I help run customer success and pre-sales here at Deepfence. And I just kind of like to point out that Owen and I have previously worked at another company called Nginx. So great to be working together again. All right, so I'm going to go ahead and shut off my video just because I have some potential bandwidth issues today. But let me go ahead and kick off this demo. All right. All right, sorry, I just had to ask, is everyone able to see my screen? Okay, good. All right, so in this demonstration, I'm going to be using the Google Microservices demo, otherwise known as the online boutique or hipster shop, to show how you can secure your GitOps pipelines using GitHub Actions and Deepfence Threat Mapper as part of your continuous integration. And then we'll use Weaveworks Flux as part of that continuous deployment. So on the CI side, I'll be using a GitHub action that listens for a push request, and this will build a Docker container image, scan that image for vulnerabilities using Deepfence Threat Mapper, and then finally push that image to a container registry. On the CD side, I'll be using Weaveworks Flux then to periodically scan my container registry for changes. And when it detects that there is a new image tag, I automatically deploy it to my Kubernetes cluster and update the corresponding manifest files. All right, so the online boutique, right? So for those of you who are not familiar with the Google Microservices demo, it's really just comprised of a series of microservices built across various programming languages and highlights gRPC and service-to-service requests. For this particular demo, I split out the front-end services, which is what you see on the screen here, into a separate GitHub repo from the remaining services so that I don't have to wait for all the microservices to be rebuilt when I push that change to the front-end service. All right, so let's say we want to make a change to the front-end service here. So I've already kind of taken the liberty to do to create a branch from master with the name v0.2.3. This is one patch release greater than the existing services that are currently running in my Kubernetes cluster. I've already staged the change that I want to make, and so I'm going to go ahead and commit and push this change to the branch. We'll go ahead and commit. And we'll go ahead and push. All right, so if we go to the actual GitHub repo itself and we go to the actions, we can see that a workflow flow is created. And if we click on this workflow, we can see that it's programmed to do a couple of things, right? So it's going to, it will show up here in a second, but basically what it's going to do is it's going to check out the current repo. It's going to prepare a Docker image tag. It's going to log into the Deepfence container registry in order to pull down the threat mapper container image. It will then go ahead and build the Docker image based on that Docker file that we pushed. And it's going to run that built Docker image through Deepfence Threat Mapper. So not only does Deepfence Threat Mapper have the ability to scan the underlying OS packages, it also has the ability to scan for vulnerabilities in language-specific stacks. So things like JavaScript, Java, Node.js, Ruby, Python, PHP, and .NET. So if the vulnerability scan fails based on whatever supplied user criteria I have in terms of CVE count or score, I will get a Slack message saying that it's failed. And the Docker image itself will not be pushed to my container registry. If the vulnerability does pass, the next step is to log into the Docker registry containing my services and then push that image to the registry. All right, so it's right here. It's going to be wrapping up the initial scan. So we'll just wait for that to complete here. All right, so actually we can see here that it actually did fail with the message that the CVE count was greater than 50. So in this case, I set my threshold for 50 CVEs total. And if it doesn't pass that, it will fail. And also we can see here as part of the Slack integration, I received a message letting me know that that particular vulnerability scan failed. All right, so if we take a look then at the Deepfence console under vulnerabilities, right, I can actually look at the information about that particular container scan, right? And I can see here that there were 71 total CVEs ranging from low severity all the way up to high. All right, and again, because the reason why this particular scan failed is it was actually detected as 71 total CVEs, whereas my threshold is set to 50. So if we click on the scan data, we can get a detailed information view about those individual CVEs that were found. So let's take a quicker look at the CVE with the high severity rating here, and just as an example. So we'll try to provide as much information about that CVE as possible, right? So in this case, we can see that this particular CVE is related to glibc. We can get the container image that it was found in, and also, like, for example, the container layer itself, which helps really kind of identify where within that Docker file we should take a closer look. We can also see the CVSS score and a brief description. So we're going to go ahead and try to provide as much information about this CVE as possible, including a link to that particular CVE itself. So if we click here and open this link, we can see that, hey, ultimately that this particular CVE was fixed or resolved in glibc version 2.31-9 for Debian. All right. So for the sake of brevity for this demo, let's just assume here, right, that I've kind of addressed some of the CVEs that were found, and I want to try to attempt to rebuild this again. So I'm going to go ahead and add that fixed Docker file back into this GitHub repo. I'm going to go ahead and do a commit and push on it. So let me go ahead and do that real quick. So if we do a git status, we can see that this Docker file has been added. So let me go ahead and add that. Go ahead and commit this. We'll go ahead and push this. So then we'll be able to go back into the GitHub Actions again and see that a new job was kicked off for this. All right, so then we'll go ahead and wait for this to complete.
Thanks, Matt. So while that runs, we'll see the same series of tests being run against the build. And we take a pragmatic approach at Deepfence. We know that it is not practical to lock down and avoid every single CVE or vulnerability within the code that you're using. Often because you might have dependencies on particular versions of a third-party component, and it's not possible for you immediately to upgrade without extensive testing. But also because many of the CVEs may not be weaponized, and the vulnerability may just be theoretical in the context that you're running the application in. As we'll see in a later demo, one of the things that we can do with the management console is illustrate how different components are interrelated. So which components are talking to which other ones, which ones have direct contact from external internet. And that way you can assess what we call the blast radius of individual errors. So you can decide how to triage and prioritize fixing particular issues or CVEs within the application. So once the build has happened, and it looks like the build now has succeeded, Matt. So yep. Richard, what happens next now that the build has been pushed out into the repo?
So from Flux point of view, the image automation controller detects that there is a new tag within the image registry for that application, and depending on the rule, whether that's semver or some regex, it sees that there is a later tag. So it will then modify essentially the YAML for that application and check out and commit that back into source control, and then from there it applies that change back into the cluster.
Great. All right, so just to kind of also showcase here, so this happens to be the private Docker registry that I'm using, and I just wanted to showcase, hey, that the build process did complete. We did not receive an indication that it failed, and we'll see here that there is a new tag being pushed to that registry. So what I've got here actually, and great, it just finally kicked off, is that here we can see that this is the Kubernetes pod, cluster itself, and we can see that the front end service, the old one, is essentially being terminated, and the new one container is being stood up, right? So if we go ahead and look at that, right? Again, we can see here terminating of the old version, and the new one is up and running. Now, we can also visually see that change as well, right? So this, if you remember, this was the original online boutique, and we went ahead and made some changes. So if I go ahead and refresh that, now we can see the online, the front end for this store has changed. So not only did I want to point that out, on the Flux side as well, we can also see here that the latest change to this repo, right, which is really the source of truth for the cluster itself. We can see here that there was a change to the registry manifest, to the manifest file itself, and we can see here that that tag was updated from v0.2.2 to v0.2.3. All right, so just to kind of quickly recap what we did in this first demo, right? What we accomplished here is we used GitHub Actions for CI, kicking off a workflow to run, to build a container image when a Git push is received. And then we used Weaveworks Flux for CD, right? Scanning that container registry for new tags, deploying the new container image to a Kubernetes cluster, and automatically updating manifest files with the new image tags. We further secured the CI pipeline, though, by integrating Deepfence Threat Mapper to scan for vulnerabilities, right? Preventing images from getting pushed to a container registry and getting deployed to a Kubernetes cluster if the user specified CVE criteria is not met. All right.
All right, thanks, Matt. So we've seen the first stage of Deepfence's protection capabilities. We can insert ourselves into the CI/CD pipeline. We can scan container deployments as they're happening and prevent containers with particular vulnerabilities from going into production. But that's only half of the security measures that you need for a production-grade, secure environment. Because there can be zero-day vulnerabilities, issues can appear with misconfigurations of the platform that you're running on, and there can be issues where unexpected behavior is happening that you want to be alerted to so that you can look into those anomalies. Deepfence's agents, as I described before, monitor and scan non-intrusively individual containers and hosts. They look at known and typical misconfigurations. We do that using our own internal heuristics and a number of open source and public guidelines and benchmarks to make sure that your production environment is configured and deployed in a way that follows best practice. And then actively, we inspect the traffic between individual containers. We look at system and application behavior, so unexpected process creation and unexpected sequences of syscalls. And we do all of this, again, non-intrusively, and feed that back to the management console for analysis so that we can use the correlation engine that we've developed to highlight if a particular sequence of operations matches what could be a suspicious event. And this allows you then to dive in and either manually triage these events, so look at and audit your containers and try and understand why the behavior is happening. Or if you wish for particular correlations and events, you can configure the Deepfence console to automatically quarantine workloads that hit those correlation triggers so that we can prevent traffic coming in and out of those containers. So Matt, let's hand back to you and we'll see some of that running in practice.
Actually helps if I unmute myself here. All right, let me go ahead and share this again. So we'll do a part 2 of this demo now. Actually, I need to show the entire screen here. All right. Okay, so in the infrastructure that I'm observing here with Deepfence, right, I've deployed a virtual machine running Apache struts. This is something that has had some well-known exploits over the year, as we kind of referenced in the beginning. So in the background, I'm going to go ahead and run a series of exploits against this virtual machine. So let me go ahead and kick that off. So in just a few moments, we'll start to see alert information being populated in the Manager Console UI, along with receiving alerts over Slack, which is actually what I'm starting to see now. And this is using the Slack integration that we have with Deepfence. So I want to take a moment here to briefly talk about what the Deepfence agent is doing in terms of runtime analysis. So it's looking at 4 different potential attack vectors: network requests through full layer 3 through 7 out-of-band deep packet inspection, file integrity monitoring, system call monitoring, and process monitoring. In a nutshell, we're able to see what goes in, what comes out, and what changes. Complete observability. You can actually see part of this observability in the topology view that I have here on my screen. Notice that a few of my Kubernetes nodes here are communicating with with GitHub essentially, right? This is actually the Flux part of my Kubernetes cluster where they're continuously looking at my repo to detect changes to that particular source of truth. I can also see here that I also have a couple of nodes that are talking to an S3 bucket. StackPath here is another one, and Cloudflare as well. So we recently added these enhanced visualization features to the topology view, display really in more detail cloud native objects such as a load balancer, storage, etc., as well as some of the well-known and popular endpoints. All right, so switching gears back to the demo again here, if we take a closer look at the alerts now, we can actually begin to break down what happened during the exploit that was just run. Right, so if we take a look at the first event that came in, this was an inbound network request. And because we're doing the full deep packet inspection, right, we're actually able to see what's in that payload itself. So if we look at the content type here, oops, actually, sorry, that was the wrong one, my bad. It's this one here. If we look at the content type, right, we can see that this content type is actually a little bit nefarious looking, right? And we can actually see that there are some Apache struts OGNL expressions within this content type header. This is essentially a key indicator. This is an Apache struts exploit. And if we look at the correlation chart below, right, we can actually see the corresponding CVE, in this case, CVE 2017-5638, which belongs to Apache struts, right? And that was picked up as part of that, it's picked up as part of the vulnerability scanning, right? Something that we did in the first demo where we integrated that as part of the CI process. All right, so we built this correlation chart here, right? Really showcasing, the severity and the CVEs that we found with the exploit that we found. But this happens to be coming across through the network. We also have some of the other attack channels that we can look at as well. So for this case, let's take a look at a file anomaly, right? This is using that file integrity monitoring that I mentioned earlier. So in this case, we can see here that a temp file was created, in this case under the, it's called pwnd.bin under the temp directory. And this particular file was modified and has executable code within it, right? We can also see some of the system calls going on as well, right? We have a couple of S traces being run. So in this case here, a user or something suspicious on this particular host attempted to run S trace. And then we also have a bunch of, well, at least one core dump as well, right? So more on the process anomaly side, right? Being able to see what changed with the processes. Now, last, I also want to show the case what we saw at the end here, which was data exfiltration, right? So if we look at this, this happens to be now a network request again, but it's outbound in this case, right? Oops, sorry, it's this one. So in this, what we're seeing here is someone actually went ahead and tried to look at what's in the Etsy passwd file, right? So sensitive information, and it's actually then trying to send this to an IP endpoint that has a known bad IP reputation, right? And we continue to build out this correlation chart over both space and time, right? So we started with just the one exploit that we saw and continually builds upon that to showcase the remaining exploits within this particular attack, all kind of pointing back again to that CVE pointing to Apache struts. So what we've seen really in this second demo is Deepfence's ability here to observe in real time malicious events coming through different attack vectors, whether it be through the network, whether it's file, system call, or process related. Deepfence has the ability to not only detect exploits that match known signatures, but also events that are not signature based. It's just for an example, like that file anomaly that we saw and the data exfiltration, which also covers potential zero-day exploits. We use machine learning not only to get a baseline of what normal operation looks like, but also to correlate suspicious events over space and time with the known critical vulnerabilities and weaknesses. ultimately giving the end user the ability not only to protect their infrastructure in real time, but also address those vulnerabilities over the long run. So something that we aren't going to discuss on this particular webinar, but we will be addressing this in a future one, is the ability to automatically protect your infrastructure based on the alerts that are being generated here. And just as a quick overview, we have what are called quarantine policies and network policies. Again, these are triggered based on the alerts that we're receiving. Now, one thing I just wanted to quickly wrap up here is on the defense agent side, right? That defense agent is, again, looking at those 4 particular attack vectors. It is doing the deep packet inspection. We are using a eBPF, so enhanced Berkeley packet filtering under the hood. So that really allows us to sit in Linux user space while having the advantages of being able to probe into kernel space, right? So we don't have to be a kernel mod. We don't have to be a proxy to do this in order, and that will, typically proxies will slow down your fast data path. We're able to do all of this out of band in real time. So with that, I'd like to hand it back to Sonia then for questions and answers.
Great, thanks guys. Thanks Richard, thanks Owen, thanks Matt. Great presentation. So we have a couple of things in the Q&A window. Richard already replied to that, but I'm still going to read that out loud for other folks to see. What should be the strategy when managing multiple configurations for multiple clusters? Can be different application environment clusters. Richard, do you want to quickly go over that?
Yep, sure. So there's a couple of options here. So if you're using Helm, you can have different values per cluster, per environments. Or if you prefer customized, then you can have different overlays per cluster. But then you also have the question around, if you're using GitOps, how many repos do I need? Do I use repos and branches? So there's a number of schools of thought on that as well, and that all feeds into answering that. And you can get repo proliferation with GitOps. So it all depends on how you do authorization and level of that authorization, whether you use branches, folders, or repos. But yeah, Helm charts or customize.
Cool, thank you very much. Okay, I'm going to go through some that we collected on the chat as well. If you scan the CI pipeline at build time, why also scan the registry before or after deployment? I guess that's going towards Deepfence, please.
Yeah, great question. It kind of sounds like a bit of a belt and braces approach, but the reality is that a lot of the containers and artifacts in your registry didn't go through your CI/CD pipeline anyhow. There are stats to show that for many enterprise apps, over 50% of the deployed containers came from third parties such as Docker Hub or from other vendors. So it's essential to scan those just as you scan the stuff that you've built yourself. In a previous life, I helped to look after an ingress controller container, and we would regularly get questions raised from the community because they would scan our ingress controller container without building it, and it matched some of the CVEs or issues that Deepfence would be able to pick up. So belt and braces, but also acknowledging that you take your artifacts from many sources, not just your CI pipeline.
Great, thank you. Can we run artifacts scanning against Helm charts? I don't know who wants to take that.
I guess this is more of a static analysis of the Helm chart, isn't it? And the declarations within it. That's not something that I've done, but I believe that there is a conf test plugin that will enable you to scan those artifacts within the Helm chart.
Great, thank you. Cool. Let me see what else we have here. How do you build approval processes for changes to the cluster if they're done through GitOps? What are some good practices there?
So the approval process is essentially at the PR level. So you can implement whatever approval process that you want from the PR and block the PR merging if those checks don't pass. And they can be whatever you want. They can be making sure that the code has been scanned, making sure that all the unit tests pass, making sure it's gone through a previous lower environment, or that you have the required number of people saying, yes, this is ready to do. But from a GitOps point of view, it is done at the PR level.
Okay, great. And I think we close it out with another Deepfence one that we had here. Isn't it enough to just build against latest for all dependencies?
So I know of some users for whom that's the policy, but the reality is that when you have limited control over all the dependencies, you want to pin to a particular minor version, particular semver, unless you've got enormous confidence in your test, your unit tests, your end-to-end tests, your smoke tests in production. So applications can end up with dependencies that can be 2 or 3 years out of date fairly quickly. The task of reconciling and resolving those and testing those can be too high. So you need a pragmatic and sensible way of identifying which older dependencies may constitute vulnerabilities and triage and prioritize which ones you need to fix.
Good, thank you. I think this is all what we have time for. We're right on the top of the hour. So I want to thank everybody again for joining us today. Thanks to our speakers. We will be sharing the recording and the slides post-webinar. So we'll find it in your inbox. And then everybody have a wonderful rest of your day. Thank you so much. See you soon. Bye-bye.
Thank you. Goodbye.
Bye.